that. That good enough? I can get to that. All right? How? How can I get to that?
Extend RI extend it and then connect to RJ.
Yeah, what I want you to do is imagine this. You see this parallel? This is running parallel. See that? These lines. See all these lines that are running parallel like this? Yes? And then with this vector, I'm going to run parallel lines like this. Good enough? You'll see it? So how could I get here? Let's see. What do I have to do to get here? If this is R1. Ri, sorry. What would I do? Try and get from here and then like this. Can I create this red vector? Can I create that red vector using this vector right here? Do y'all see this or not? Let me put something next to this so you can see it. The thing is, if I take a vector like this in standard two-dimensional space, it's easy to get to it. If you grid this out, running like this, it's easy to get here because you take I however many times, right? And then J however many times to get up. But you're basically moving along left and right in these increments, and you're moving up and down in increments. The same thing here. If I have these two standard vectors, as long as I stay within this grid, which is not squared up anymore, can I still get to this point? Yes. I mean, there's a way to do it. There's a certain multiple of this, right? I really want to try and show it. How about I do this? How about I take this red one and I point it in the other direction? Could I do that? And then eventually, if I make it long enough, wouldn't I be able to come back up with the blue vector to here? Yes? That's the way I would do it. That might be stretching it a little bit too far. But there is a point to me saying that, and this is for the linear algebra people. These two vectors in two-dimensional space are also called a basis for the space. They're a basis because you can draw any vector in that space with those two vectors. A standard basis, I hat, j hat, are so special because they have a couple of things going on. First, we said the length of them is what? 1. The length of them are 1. But they're also perpendicular to each other. And so in linear algebra, what they'll refer to this as is what's called an orthonormal basis. So I and J in linear algebra are referred to as an orthonormal basis. Ortho stands for the word orthogonal, which we're going to talk about today. Orthogonal means perpendicular. So you have two basis vectors that are perpendicular to each other. Normal means that they have unit length, and basis means they span the entire space. That's a very special basis, and that's why we like to use it, because it's an orthonormal basis. But this is an example of a basis, but it's not an orthonormal basis, because these don't have unit length, and they're not perpendicular to each other. But it still spans the space. Sorry, I'm off. I'm going to come back. Sorry, went off on a little tangent there. All right. Oops. Now in three-dimensional space, there's a little bit of a change. We just have a third component. So I hat is now, instead of 1, 0, it's 1, 0, 0. J hat is 0, 1, 0. And K hat is 0, 0, 1. And those vectors, 3D-wise, look like this. You have I comes down the x-axis, J goes down the y-axis, and K goes up like that. So this is I hat, J hat, K hat. And they all have unit length, right? Are they all perpendicular to each other? Yes, they are. And do you think you could draw a vector in here that I couldn't get to using those? It's impossible. Any vector you draw, I will be able to find it using some combination of these three vectors. So again, in three-dimensional space, this is an orthonormal basis. But for us, we just call them the standard basis vectors. All right, that's just some terminology. So this is a very, very simple example, all right? Let's not make it complicated. Write this V as a linear combination of standard basis vectors. Very simple to do. 2i plus 3j minus 5k. When I say I, j, k, please understand I mean I hat, j hat, k hat. That's it. We're done. Now, if someone gives you this, can you go back to that? Pretty simple, yeah? But just remember what it means. It means this. Right? That's what it means. It's three scalar multiplications of three different vectors, and then you combine them all together, and if you were to do that, you would get back this vector. But isn't this a lot easier to write than this? So I think that's why we prefer it in physics, shorter notation. But mathematicians, oh, we prefer that. That's even better. All right.
Will you always refer to it as standard basis vectors, or will you use like unit vector notation?
You mean if you're ever asked to convert like this?
Like
Yeah.
if you want a certain way, would you always just say standard basis vector notation?
I would specify use standard basis vectors if I wanted it. And I would never take off on a problem if you like this notation. If you prefer this, go ahead. But I'm going to use this as little as possible. I'm going to be up here using the angle brackets. When you do your homework, the problems they give you a mixture of both. All right? Is that it? Okay, 10-2 is over. And everyone knows where the homework for 10-2 is, right? Okay. All right, let's talk about now the dot product. All right, so there are, again, three different multiplications. There's an entire section here dedicated to one type of multiplication called the dot product. And here it is. Ugh. All right, so given two vectors in two-dimensional space, so if we have two-dimensional vectors, u and v, then u dot v is defined to be v1 u1 plus v2 u2. So all you're doing, I want you to see this, is you're multiplying the first components together, right? You're multiplying them together, and then you're adding to that the second two components together. So you're taking two numbers, multiplying them, two numbers, multiplying them, and then adding them. So the answer should be a what? A number, right? The dot product is the sum of the products of the components. It's vital to notice the dot product yields a number as the answer, not a new vector. This is strange because anytime we've had multiplication in the past, it's never behaved this way, right? If I take, again, the number 4 times 5, what was your answer? 20. A number, right? Two numbers, they put them together, you get a number. Great. Even if you take two functions and multiply them together, you always got a function, right? Now we're taking two vectors, we're multiplying them together, and we're getting a number, something that isn't even a vector anymore, right? That's the definition of a dot product. So we'll use this bolded dot to represent dot product instead of the regular multiplication dot. In three-dimensional space, it's the same story. You take the first components, multiply them, then add to that the second components, and then add to that the third components, multiplied together. Again, the answer is going to be a number. Weird, right? The natural question would be, what does that number represent, right? Like, we all know what 3 times 5 is, right? You can imagine that as being like 5 groups of 3. And so it makes sense that the answer would be 15, right? But what does a vector times dotted with a vector being a number, what does it represent? What does that numerical value mean? Yeah? Hopefully it means something, right? Not just some arbitrary number. Okay, but that's the mechanics of it. So a quick example. What's u dot v here? So I'll do this once, long notation. 2 times -3 plus -3 times 4 plus 5 times 7, right? That's what I'm doing? So -6 minus 12 plus 35, which is 17? You'll notice this when I'm doing if you watch me doing the homework videos, you'll see when I get to, my brain just completely just turns off. As soon as I see arithmetic, my brain's like, I guess it's kind of like, you know how computers like save memory for certain tasks, and like my brain just, as soon as it sees arithmetic, is like, do not commit effort to that, and shuts down. It's just arithmetic, yes?
So that number's scalar, what does it represent?
Yeah, I'm going to answer that. But I mean, it is important for us to wonder what it is, right? Let's just first make sure we can compute it. We can compute it? Yeah, we're happy? Okay, let's now figure out what the hell it means. So, well, before I get to that, some properties of the dot product. If you dot a vector with itself, u dot u, you get what? Its length squared. What? Okay, I take some vector u, which I'm calling u1, u2, right? If I dot it with itself, that means I'm going to take the vector u again, right? And let's dot it. So what's u dot u? By the definition, it's u1 times u1, right? Which is u1 squared, plus u2 times u2, which is u2 squared. Does that look familiar? Well, what's the magnitude of u? The square root of u1 squared plus u2 squared, isn't it? Isn't that the definition of the magnitude of u? Right? If I gave you this u and I said, hey, well, how big is that? How long is that? You would say that, right? But if I square this, right, isn't it this? See that? So that's where this is coming from. You take a vector, you dot it with itself. It gives you the length of the vector squared. That's only if you dot it with itself, though. Now, this property is the property that we use with standard multiplication of numbers. 3 times 4 is the same as 4 times 3, right? We call that the commutative law, not commutative. Commutative property, right, that you can flip multiplication around. You can do it with the dot product. It's going to turn out for the third multiplication, which is next class, the cross product. Cross product is not commutative. So we're going to learn that next class, that you can't flip cross products like that, but you can do it with a dot. That's good to know. Excuse me. Distributive property over addition. If you take two vectors and you add them together, what should you get? A vector, right? And then you take that new vector and you dot it with this vector. Whatever that answer is, it's the same as you dotting the u with the v, then adding the u dotted with the w. So it's almost like you're distributing the dot product over addition. That is a property of dot products. We could verify it, but we're just going to take it on faith.
If you add them first and get the result, can you just multiply them by the...
Dot it with that, yes. Uh-huh, yes. Wait, hold on. What are you saying?
Yeah, dotting it. Yeah, you add those together and then you...
Dot. You take that result and dot it. You can do it that way, or if you want, you can dot these. That'll give you a number. You dot those, that'll give you a number. You add them together, you get a number. Those two sides should be the same. If you scale a vector and then dot it with some other vector, you don't have to worry about the scalar. You can dot the two vectors first, then scale it. You can even move the scalar to the other vector. It all doesn't matter. So dot product is very well behaved. It lets you follow a lot of the rules that you had with standard numbers. Look at this one. The 0 vector dotted with v is 0. The number 0? The dot product of two vectors is always a number, isn't it? So is this correct notation? Yes, that is correct. This would be incorrect. That is not right, because that's not a number, right? So that is correct. Would this be correct? No, because you can't dot a scalar with a vector, right? That's a scalar, so that wouldn't make any sense. Your homework, they're going to ask you these things. They're going to give you like these different symbol representations. They're going to ask you, does this make any sense at all? Like, could you compute this? And you have to know when you can and can't. Y'all hanging in there?
Yes.
Thank you. I don't really feel like doing that. Unless we want to do it fast. Do we want to do it fast? Let's try and do this fast. All right. Can you tell me very quickly what 3u is? Okay, so it's -9, 12. Okay. And then I'm going to do what? Multiply, so dot product with VW. What's V plus W? 6, -3. Yes?
So the W is meant to be a vector then, right?
Yes, that's bad notation here. Hold on, let me correct it in my notes. Thank you for pointing that out. All right, so then dot these. What do you get when you dot these? So -9 times 6, -54, and then plus, and then 12 times -3, which is -36, and you get -90. Okay, -90. Okay? Now you could have used properties on this. You could have, if you wanted to, you could have done 3u dot v plus 3u dot w. And if you would have done that, you would have also got -90. But I just did it, I guess, the way that most people would have. Take care of this, put them together. All right, we still want to know what the hell this dot product means, right? So we have this extremely important theorem. It's called the dot product theorem. Now, I'm not proving this theorem. I believe the book does. I could be mistaken. Hey, I forgot last time to pass around the sign-in sheet because I do take attendance. So please find your name. If your name's not on this list, write your name on the bottom. And then just initial in the date. And if you were here last time, just initial. If you weren't here last time, I guess you could act like you were. It doesn't matter. But just do today and last class, please. So 2 initials. And when this goes around, make sure you move it around the room, okay? Don't just let it sit on your table. So I'm not going to prove this theorem. Let me see if they prove it in the book. Yes, the proof is in the book. So since it is in the book, I won't commit time to it. It's kind of cool. They use some law of cosines and things like that. It's on page 552. Some proofs in this calculus book just can't be done because the proofs are too advanced. When the proofs are easy enough for a student at this level to follow, they'll put the proof right there in the section, which in this case they did. So I would encourage you to go and take a look at it. I'm not going to commit time to the proof. But we are definitely going to put a huge asterisk next to this and say, guess what? We are going to put this into our memory banks. So you may be like me and not be able to do negative 16 minus 54 plus 13 because your brain just says, who cares? This one you need to put in there, okay? So reserve space for that. U dot V is equal to the magnitude of U times the magnitude of V times cosine theta. Now these are just regular scalar multiplications in there, okay? They're not dots. Is that a question?
So whenever you write them in 3 dimensions, does it remain cosine theta? And
Yes.
having another magnitude?
Nope. These vectors, right now I'm not telling you where these vectors live, right? So these could be 3-dimensional vectors. This is what's amazing about this theorem. It doesn't matter where your vectors are. 2D, 3D, 4D, doesn't matter where they are, okay? If you take two vectors, all right, here they are. 2 vectors, different lengths just for fun. Okay, if I take a vector U, I take a vector V, sitting there in 3-dimensional space, and I dot them, what happens is I take the length of this one and the length of this one and multiply that answer together, and then I take cosine of the angle between them. So what do I mean by cosine of the angle between them? Well, they're 3-dimensional, right? So I can move them along without, as long as I don't change the direction, right? So I'm going to just move this one to match up right there. Do you see that? Now if we look at this in a plane, like this flat sheet, I'm pointing it at you because you're asking, right? Everyone's see that plane that I've made right there? If we turn that plane flat, this is the angle we're talking about, all right? So if I take any 2 vectors, no matter what space they're in, and I attach tail to tail, right? And then look at that flat sheet of paper that they both go through, like that, that's the angle, theta. Understand that? So this theorem connects the dot product to the length of the vectors and the angle between them. Now let's look at some results of this. There are some big time results of that theorem. First of all, if we're given 2 vectors, the angle between them must be between 0 and pi. I broke my vectors. I should have kept them here. If I take 2 vectors, it doesn't matter if we're on a flat sheet of paper or in 3-dimensional space, the angle between them must be between 0 and pi. So let's imagine this. I take these 2 vectors. That one's pointed over here. This one's pointed over here, right? If I take them and go tail to tail, right, the angle between them is between 0 and pi, isn't it? Yes? So when we say the angle between them, there's going to be a smallest angle. Because you could go this angle back this way, right? That would be bigger than pi. But the shortest, the smallest angle is this one. So what about if they're pointed exactly in opposite directions? The angle between them is pi, isn't it? And it's okay to be pi. That's why it's less than or equal to. So it's either this, or you could also have what? Parallel vectors that are pointed in the same direction, like this. What's the angle between those? 0. So no matter what, if someone gives me 2 vectors, the angle between them must always be between 0 and 180, yeah? Okay, now let's consider the cosine function from pre-cal. So what I'm doing is I'm about to look at this in more detail. U dot V equals magnitude of U, magnitude of V, cosine theta. Think about cosine theta from pre-cal. If theta is 0, cosine is 1? Yeah? So if the angle between the 2 vectors is 0, then what does the dot product represent? If the angle between 2 vectors is 0, what does the dot product represent? This is a 1 now, isn't it? So it's just what? The dot product is just their lengths multiplied. That's all it is. Understand? So if your angles are pointed in the same direction, then the dot product represents the product of their lengths. It's a number. It's the length of each one multiplied together. Now let's look at another important angle. What if the angle between the 2 vectors is pi over 2. That means that they're perpendicular, right? And what happens to cosine at pi over 2? Cosine of pi over 2 is 0. And therefore, the lengths don't matter, right? The dot product is 0. And this is probably the biggest result we're going to have. I think I'm going to put it on the board here in a second. But what if you have two vectors and you're trying to figure out if they are perpendicular or not? Well, what do you think? If I give you two vectors, say, are they perpendicular? How do you think you'll be able to check?
Take the dot product.
Take the dot product. What does it need to be? 0. That's it. That's the check to see if two vectors are perpendicular. It's beautiful. It's simple arithmetic. If you want to know if two vectors are perpendicular or not, all you have to do is take their dot product. If the dot product is 0, they are perpendicular. Now, another word for perpendicular, I don't have it here. I have it in a second. Never mind. OK, so let's move on. Oh, yeah, there it is. Right here. This is a big part of the notes. That's why I've highlighted it here. Two vectors u and v are said to be orthogonal, which means perpendicular. All right? If and only if u dot v is 0. Now, what does if and only if mean?
It's
Yeah, I've talked about this with different students who have had me in the past, but I know there are some people who are wanting to be math majors and stuff. Anytime you see if and only if, it's an important thing. It means a double implication. It means that it goes both directions. I'll give you an example. If you're from San Antonio, then you're from Texas. Is that true? If you're from, let's just say you're legally in San Antonio, right? You're registered, whatever. Let's not get into these different arguments. Okay, you live in San Antonio, you live in Texas, yes? So we could say this, San Antonio resident implies Texas resident, yes? Does it work the other way around? If you're from Texas, does that mean you have to be from San Antonio? No. So this would not be a double implication. It doesn't work both directions. If it does go both directions, it's called an if and only if statement. It's a double implication, and usually we put a double arrow but going in both directions between the two statements. Okay? That's what this is. This is saying if somebody gives me two vectors, right? Where are they? If somebody gives me two vectors that are orthogonal, guess what? The dot product must be 0. And if somebody gives me two vectors and their dot product is 0, then they must be orthogonal. They must be perpendicular. So both directions. Do you understand the subtle difference in there? And that is a huge deal, because this is going to be our standard way of checking, like I just said, whether or not two vectors are perpendicular. Orthogonal. Now, go back to the formula that I erased here a second ago. Going back to that good old dot product. Does everyone agree that the magnitude of u is a positive number? The length of a vector is positive? Should be, right? The length of this vector should be positive? Yes? So the only thing that could possibly make the dot product become a negative number is the value of cosine, isn't it? And that's what the next note says. Here it is. When your theta, when the angle between your two vectors is between 0 and pi over 2. So if your angle is something like in here, what is cosine of an angle that's between 0 and pi over 2? Is it positive or negative? Positive, right? So if the angle between your two vectors is between 0 and pi over 2, then this will be a positive number, and the dot product therefore is positive. Now, if your angle between your two vectors happens to be bigger than pi over 2, right? Then what's going to happen? Cosine of that would be what? Negative. So your dot product would be negative. And I have an illustration of that on the next animation. Right here. So does everyone see these two vectors? Okay. What I'm having the computer do is do their dot product. Right now, do you see that the dot product is negative 2? The computer's doing that in the background. Yes? Well, what is it being negative tell us? That the angle between them is obtuse, bigger than pi over 2. Automatically, we know that. But if I take this vector and I move it over here, oops, then look at the value of the dot product. What's happening to it as I move it over? Still negative, right? What's it getting closer to? 0, huh? I wonder why. Because when I get perpendicular, what's going to happen? It is 0, right? And then as soon as I get smaller than pi over 2, it's now a positive dot product, right? And that's because I have an acute angle between the two. Do y'all see the connection? Y'all see that? Okay. If I point this in the same direction, what's going to happen if I make this on that circle and I bring it down right on top of the other one? What should the dot product equal? Should be 1, right? Because it should be the product of their two lengths, shouldn't it? And 1 times 1 should be 1. What if I take that and I drag it out to 2? Should be 1 times 2, which is 2. Pretty close, 1.99. Take it out to 3. The dot product is the length of this one times length of this one. What happens if I take this one and I drag it all the way around to the other side to negative 3? What do you think it's going to be? It's the product of the two lengths again. 1 times this length 3, but because it's an obtuse angle, it's negative. Make sense? Now, you could take this out and do it in 3-dimensional space, but it's so much easier to illustrate it in 2-dimensional space. Man, where's the time go in this class? This one's almost a trivial example. What's the dot product if I give you the lengths of the two vectors and the angle between them? Is this even worth doing? U dot V is magnitude of U, magnitude of V, cosine of the angle between them. What's the magnitude of U? 3, magnitude of V, 7, cosine of 31 degrees. Get your calculator out. Make sure you're in degree mode. What do you get? About 18? Is that what you said? Okay. Well, that's good because it being a positive answer, you know, the angle was acute, so that kind of makes me feel better that that's right. Are these two vectors orthogonal or not? No? Why not? Okay, so all we have to do is check the dot product, right? Take the dot product, see if it's 0. So what is, do I have to do U dot V or can I do V dot U? It doesn't matter which one I do, right? Because it's commutative? Okay, so dot it, let's see. 2 times 6, right? That's what we're doing. Plus 4 times negative 3, which is 0. Are they orthogonal? Yes. Right? Isn't that a nice check? I mean, come on, that beats what you might have wanted to do, which was draw the first one and then draw the other one and go, yeah, I think that's orthogonal. Or try and do some sort of Pythagorean right triangle hope for the best thing. That's not fun, right? You would have to like check the length of this and then the length of that, and then you would try and get the length of this, and then you'd try and confirm. Part of your homework was that. You don't need it anymore. It's easier now to check if a triangle is right by just looking at the vectors. How many of you did the homework where you had to see if the triangle was a right triangle or not? Anyone do that? So they gave you like 3 points in space, right? And then something like that, and you were saying, is that a right triangle? So what you did is you found the length of each of these sides, right? Okay, no longer necessary. If I want to know if that's a right angle, all I do is I come up with this vector, I call it U. I come up with this vector, I call it V. I dot them. If it's 0, it's a right angle. I don't need to check lengths. Much easier this way. Now, let's say that you dotted those and it was 0. You'd be right triangle done. What if it wasn't 0? Well, then you would just do this vector and dot those. If it was 0, it's a right triangle. If it's not, then move on. You have to do this one and this one. But the dot product is much easier to do than all that other stuff. All right, so here's something a little more abstract. You're given two vectors. U is the vector 2, negative 2, 6. The vector V is A, 3A, negative 2A. And just for fun, let's just make this one A squared. And find the A such that these are orthogonal vectors. I don't even know if there's going to be an answer. Okay? Because I just tweaked the problem. It may not be possible. So what do we need? We need, right, that U dot V be equal to 0, right? That's what we need for these to be orthogonal. So what is U dot V? Well, 2 times A, right? So 2A plus what? Negative 6A squared or minus 6A squared. I'll put it like this. And then the last thing, minus 12A. Is that equal to 0? When is that equal to 0? That's what I need, right? Shit. Let's see. I don't know if we're going to be able to get this. This is negative 6A squared minus 10A equals 0, right? Combining like terms. And this is a quadratic. It factors pretty easily, doesn't it? A is factored out, or how about, what do you want to factor out? A, negative 2A, and be left with 3A plus 5 equals 0. Agree with that? Can you give me the two solutions? A is 0, and then A is negative 5/3. All right, so let's look at A is 0 first. If A is 0, then V is a 0 vector, right? And if you dot the 0 vector with anything, you're going to get 0, right? That's weird. Think about that. The 0 vector dotted with any vector should be what? 0. That means that the 0 vector is orthogonal to every vector, right? That's weird, though. So when we talk about orthogonality, we always say two non-zero vectors are orthogonal if and only if dot product is 0. So we always want to be playing with vectors that are not the 0 vector. So this should happen. The fact that this happens isn't a surprise. If we just make this the 0 vector, we're always going to get dot product of 0. But there's another solution that's not trivial, and that's this one. So I'm claiming that if A is negative 5/3, that should work. So let's go back and rewrite that vector, V. Negative 5/3. And what? We have to do 3 times negative 5/3 squared. So what's negative 5/3 squared? 25/9 times 3. 75/9. Which is, well, I'll just leave it 75/9. Who cares? We could reduce that, right? And then negative 2 times this, which is 10/3. Y'all with me? All right. What we are hoping for is that if I dot this with U, I should get 0, right? Where? The 3 is on the top, though. The 3 is like a 3 over 1. So the 3 goes across the top to the 25.
Right, 75. But then when you square the 3,
Hold on. So you square this first. 25 ninths. 3 times that, 3 goes across the top, 75 over 9. 3 over 1. So that's right. Is that what you're referring to? Okay. We all good with this? Anybody check it? We're out of time. Anyone check it with you? What happens if you dot this with you? Can we dot it real quick? What's 2 times that? Negative 10 thirds plus, what's negative 2 times that? It's negative 150 over 9, and then what's 6 times this? 60 thirds. Get a common denominator? Or just reduce that. I guess we never reduced it, so what is this reduced? 50 thirds? There we go, we're done. That's 0, isn't it? Right? This is negative 60 thirds plus 60 thirds, that's 0. All right, so at least get through your 10.2 homework. We're into 10.3. See how much further we have. Yeah, we still got some more important stuff in 10.3. But we'll finish 10.3 next time for sure, and then we'll get into cross product. That sign-in sheet get around to everyone? Okay. All right, everyone. Have a great rest of your day. See you Wednesday. And try and get to the. Here, hold on, let me get this.